A very warm good morning, everyone. Powering just a dozen of light bulbs with the help of two giant water wheels, and that too inconsistently, was the idea behind the very first power system ever established in this entire world. This was brought into existence by great Sir Thomas Alva Edison. But you know what? Today, we stand in a world which has one of the most complicated power system ever designed by any human being. It can do wonders with the system we have today. But the question arises, is the system which is existing enough for our needs? Science is but a stream of water that never stops flowing. And that's why development in power system cannot be limited to any extent. We still want to make everything much more efficient and smarter for the generation yet to come. This exactly brings us to the purpose of the workshop. With the enormous need and scope to turn the existing power system into a smarter one, you require a very crisp understanding and knowledge of the technologies that are emerging and helping to transform the existing system. With the end of this workshop, you would have a thorough understanding about the emerging technologies that are making the power systems smarter, so that you can easily dwell in any of these technologies further and create a better tomorrow. A detailed description about the workshop will be put forth further. Let me initiate the beginning by welcoming some of the very important personalities without whom the workshop would not have been successful. I welcome special chief guest, Dr. M. Ramamurthy sir, on the stage with a big round of applause. He served as a Director General in CPRI Hyderabad. I request a pleasant present to be presented to the professor. You all might know him as an author of several books which served a very important resource for all the electrical engineers around. It is the time to welcome Director Sir Professor N.V. Ramana Rao on stage amid a big round of applause. I request the gift to be presented to the professor. With this, I request our guest of honor, Dr. D.M. Vinod Kumar sir, who is a higher administrative grade professor in EEE department, to show his presence on the stage. Sir, please. The department was pleased to have this knowledgeable program organized on your superannuation, sir. Now I welcome Head of the Electrical Engineering Department, Professor B.L. Narsimha Raju, sir, on the dais with a big round of applause. A big round of applause is appreciated. Fire represents luminance and brilliance. It acts as a dispeller of darkness. I request all the dignitaries to light the lamp and dispel any stance of darkness. Please, sir. Tamsoma Jyotirgmaya means taking you all from darkness to enlightenment, is what is symbolized by illuminating the lamp. Now, it's time for all of us to be more enthusiastic about the takeaways that are being made from the workshop. For this, I would request the head of the department, Professor B.L. Narasimha Raju sir, to show his presence on the dais and and give you all an overview of the workshop. But before we present you the national song, please be prepared.
Vande Mataram, Vande Mataram, Sujalam Suphalam, Malayaj Sheetalam, Sasya Shyamalam Mataram, Vande Mataram, Shubhra Jyosna Pulakitayamini, Pullakusumita Drumadala Shobhini, Suhasini Sumadhura Bhashini, Sukhadam Varadam Mataram, Vande Mataram, Vande Mataram.
Nation is what to be served first. And now I request Professor B.L. Narasimha Raju sir to give you all an enthusiastic overview of the workshop we are going to conduct. Sir, please. A big round of applause is appreciated.
Respected dignitaries, today's chief guest and keynote speaker, Professor M. Ramurthy Garu, today's guest of honor, our beloved director, Professor N.V. Ramana Rao Garu, and the main guest of honor of today's function, Professor D.M. Vinod Kumar Garu, and all the professors, all my faculty colleagues, and my students, and all other registered participants, offline as well as online, and research scholars present here. Good morning to each one of you. And my heartfelt thanks to you all for beautifying this inaugural function of two-day national workshop on emerging trends in power engineering in the honor of Professor D.M. Vinod Kumar, Professor of Ag, Electrical Engineering Department, on his superannuation on January 31st, 2023. So on behalf of the Electrical Engineering Department and my own behalf, I am glad to share with you all that this program is organized in honor of Professor D.M. Vinod Kumar sir, Professor Ag of Electrical Engineering Department, on his superannuation on January 31st, 2023. After his longest 41 years of finest, outstanding, and notable service that witnessed the benefit of immense contribution in academic, research, and developmental growth of the institute, of the department, and the institute at large. And this program is planned in a very short duration, just 15 days back, and given the publicity for registration on 20th January, just 10 days back, with a bit worry and doubtful for grand success, but I am very delighted to place in record and say that the registration is turnout is 422 in a very short notice. So that is simply amazing. And this is certainly because of two reasons. One is the witness for the popularity of Professor D.M. Vinod Kumar sir, and the second is the renowned experts with their topic of finest knowledge in their field. So these are the two reasons which attracted so many participants in a very short duration. Also, all these will only possible with the finest experts' contribution for that matter. Hence, my heartfelt thanks to all our distinguished stalwart academicians and researchers, Professor M. Ramurthy sir, and Professor S.C. Srivastava, Professor Raja Rao, Professor Akshay K. Rathore, Professor Anurag Srivastav, Professor Surendra Reddy, for their kind acceptance despite their busy schedules to contribute to this our two-day workshop as a resource experts, that too in a very short notice, without which our program would not be a success one. Once again, my heartfelt thanks to all our distinguished professors for making our two-day workshop with a grand success. And now the main objectives of this workshop is to emphasize our participants in learning state-of-art technologies deployed in power system operation and control, and motivate to work in the modern research domains. Also to confer the recent trends and technologies for smooth operation, online monitoring, and control of power distribution transmission systems, to enrich the participants with knowledge in various aspects of emerging trends in power engineering. In view of all these objectives, this workshop is designed to discuss the emerging trends in power engineering, to encourage the professionals and the research engineers, academicians, to enhance their research and academic skills. In particular, followed by the keynote address on the theme of the workshop by Professor M. Ramurthy Garu, the other topics of prominent topics is wireless power transfer and current fed technology for mixed source EV charging systems, issues and solutions by Professor Akshay Rathore, Singapore Institute of Technology, Singapore, through online mode. Followed by a smart distribution network sharing few field experiences by Professor S. Srivastava, IIT Kanpur. And then the trends in power system operation and control by Professor Anurag K. Srivastava, West Virginia University, USA, through online mode. And then followed by the introduction to AI and its applications by Professor Raja Rao, Mahindra University, and he is also a chairman and managing director of Vision Labs, Hyderabad. And finally, the optimal techno-economic operation and hybrid energy systems by Professor S. Surendra Reddy, Woosung University, South Korea. These are the main focus topics of this two-day workshop. So with this, I hope that all our loved participants, definitely they will make use of this opportunity of this two-day technical fest and get benefited immensely out of these two-day discussions. So with this, once again, I wish you all the participants and all the audience, all the attendees present here and grace this occasion for the success. Thank you all, thank you one and all, thank you. Yeah. Further, I will take further the pleasure. It's my pleasure to introduce our Department of Electrical Engineering to the audience. The Department of Electrical Engineering is one of the oldest departments of then REC Warangal and now NIT, National Institute of Technology, Warangal. Established as one of the major departments of the institute, since its inception in 1959, the Department of Electrical Engineering has been actively engaged in teaching and research in diverse fields of electrical engineering. And at present, so we have 31 faculty members are working in the department. The faculty have the expertise in various fields of engineering, electrical engineering, to name few, such as power electronics and drives, power system deregulation, power system engineering, power electronic converters, drives, control of special machines, renewable energy systems, converters for LED lighting systems, multi-level inverters for open-end winding, induction motor drives, application of power electronics to power quality improvements and industrial drives, and DSP control drives, and application of ANN and fuzzy logic in power engineering, and data science in power engineering. So these are the major areas where our faculty has expertise and working in the department. And the Department of Electrical Engineering currently offers BTech in Electrical and Electronics Engineering, and MTech in Power Electronics and Drives, and MTech in Power System Engineering, and MTech in Smart Electric Grid. In addition to this, department also offers the PhD program in all the major fields of electrical engineering, and also the self-finance programs in MTech, PG diploma, and PhD have been started since academic year 2021-22. Now at present, 175 students are admitted through JEE in BTech and 95 students through GATE for MTech programs. And also at present, the more than 90 research scholars are working for the PhD program in the department. In addition, the department is elated with the finest research growth supported by the Ministry of Education, then Ministry of Higher, MHRD, Government of India, sponsored research projects from various prestigious schemes. To name fewly, Imprint India, Spark, SCRB, DST, PIST, CPRI, MSME, etc. And these sponsored projects are to the tune of more than 5.5 crores at present. Also, I am very happy to share that very recently the DST PIST project has been sanctioned to our Department of Electrical Engineering for a cost of 94 lakhs. Also, at present, the 9 junior research fellows are working in the department under the various research projects. And the department has a state-of-art equipment such as, to name few, programmable DC, AC power supplies, programmable solar simulators, high-end and mixed signal oscilloscopes, digital storage oscilloscope, power analyzer, multi-inverters, multi-level inverters, and hardware in loop, hardware development kits, and so on, etc. Further, the department has a strong industry interaction and has been involved in consistently handling various consultancy projects for various industries, like lift irrigation power projects of Government of Telangana and Andhra Pradesh. And also the department has an MOU with the various organizations such as Central Power Research Institute, Bangalore, ABB, Power Product System India Limited, Bangalore, Power Grid Corporation of India Limited, Power System Operation Corporation, POSACO, now known as Grid India, to carry out the collaborative research projects in the department. So the department also participates in the student exchange program with the IIT Delhi as well. And furthermore, with respect to the outreach activities, the prestigious faculty development and training programs have been sanctioned to the department, sponsored by Government of India under various prestigious schemes, namely like GAN, Spark, AICT Atal, E&ICT, TLC, Teaching and Learning Center, so which is sanctioned to our institute under the scheme of Pandit Madan Mohan Malviya National Mission on Teachers and Training. And also, in addition to that, the institute is also have a continuous education program and self-finance programs which can be organized by the department faculty. So through which our department faculty contributing to improve the technical education in various domains of electrical engineering community in the region and across the country as well. Apart from this, the department faculty actively contributing towards the various academic and research activities to the community of technical education across the country. Also, the department has a very good placement record and heritage of few of our alumni occupying in various top positions in the country as well. So all these related growth and achievements towards the benefit of our students is due to untied and sincere devoted efforts of our beloved colleagues. Hence, I am very happy to place all these on record and also congratulate all my beloved colleagues and research scholars of our department and all other institute faculty, staff for their kind cooperation and support, for their efforts and support for successfully organizing this today national workshop in emerging trends in power engineering in the honor of Professor D.M. Vinod Kumar on his superannuation of electrical superannuation on 31st January 2023. So with this, with great and best regards, thank you all.
Thanks a lot, sir. The description of the department was very accurate, and your description of the program has tremendously increased the zeal to learn. With so much enthusiasm in all of us, something which is still required is a blissful wisdom. Thus, I request the guest of honor, Professor N.V. Ramana Rao sir, to address the gathered audience with his profounding wisdom. Sir, please. A big round of applause is appreciated.
A very distinguished chief guest, Professor M. Ramamurthy, former Director General of CPRI Bangalore. Today's guests of honor, Professor D.M. Vinod Kumar, Professor S.J.G. in the Electrical Engineering Department, Professor B.L. Narsimlu, Narasimha Raju, the head Electrical Engineering Department, my dear deans, advisors, faculty members from Electrical Engineering, and my dear students. At the outset, let me congratulate the organizing team, the faculty and research scholars, and the chairperson of this two-day national workshop, Professor B.L. Narasimha Raju, for organizing a workshop in honor of Professor D.M. Vinod Kumar, who will be superannuating on January 31st. So normally, whenever some professor retires, we have a customary here that we organize a seminar and also talk about his achievements and contribution to the teaching field. As far as Professor Vinod Kumar is concerned, I had a long association with him for the last 5 years since I was a director. And I can tell you that after I have become the director, I have taken his advice in many things, and we have been interacting. He has been member of several committees. He assisted me in solving many of the issues of the institute. He's a renowned teacher, and I'm happy that the department is organizing this two-day national workshop in his honor on a topic of great relevance, emerging trends in power engineering. Especially, power engineering has gained a lot of importance because of the emergence of electric vehicles. The whole electrical engineering department, how to store, how to transmit power so that, it can be. So this is an area which has got a lot of future, and I'm sure that the deliberations in the workshop will help all the young participants who are gathered here to learn more about the new developments in the field of power engineering, in which Professor M. Vinod Kumar is an expert. Professor M. Vinod Kumar had a very illustrious academic career, professional career. He has a lot of publications, a lot of citations. He has guided many students. I first met him when we were both sitting in front, went for the interview for the director post. So, and we were almost in the same panel. So he's a very eminent man, and I think I don't belong to this subject, so the less I talk, the better, especially in front of people of electrical engineering. But I can talk about, his retirement. So normally if somebody retires or superannuates, we will say that he'll have no more tension, he'll have only pension. He'll have only pension and he'll have only vacation. So now we have to see what Professor Vinod Kumar has decided and what the department has decided to see that he continues to serve the academic community. And I'm sure that he's very active in research, and still he's guiding many students. Actually, tomorrow is the retirement superannuation function, but since I have another NAC inspection in Chennai, I will not be able to attend, so I made it a point that definitely I should come for the inaugural. So thank you, Professor Vinod Kumar, for all the services that you are rendered to NIT Warangal and to the student community, especially to the Department of Electrical Engineering and in general to the administration of NIT Warangal. I wish you all the best in all your future endeavors. Thank you very much. Thank you.
Thank you very much, sir, for your thoughtful words. Now I request Professor D.M. Vinod Kumar, sir, to embrace the dais. Sir, please.
Very good morning, all of you. First of all, the dignitaries on the dais, Professor M. Ramurthy Garu, and our beloved director, Professor N.V. Ramanarao, and chairperson of the program and head, EED, Electrical Engineering Department, Professor B.L. Narasimharazu, and organizing team, faculty, staff, and research scholars of the department, guests, participants, and my beloved students. On my behalf, I extend warm welcome to the participants of the National Workshop on Emerging Trends in Power Engineering. This emerging trends in power engineering, I fascinated very lot because after coming from IIT Kanpur, I introduced several courses, that is cutting edge technology subjects. Like first I introduced in the United Andhra Pradesh, Native Warangal, put together that neural networks, that is artificial intelligence techniques in power systems or electrical engineering. And after that, I slowly started, that is wherever new things are coming up, that state-of-the-art subjects, like smart electric grid. I introduced the subject, and for some deregulation. And as on today, recently, that is 2-3 years back, because I'm passionate, that is because of emerging trends, I started machine learning. That is still, I'm retiring tomorrow, but my brain, because most of the time the neural network works based upon the brain, that we are mimicking the brain. Therefore, what is that? I forgot. That is this emerging trends, that is machine learning. It took a lot of time for me for preparation. Therefore, we want to have state of the art. First of all, we should have some interest. When interest is there, automatically the brain will capture. When we doesn't have any interest, it will not capture anything. Therefore, we should have some interest. Then we can learn, we can expand. Therefore, whatever the heights we want, we can reach. And one more thing, that is out of my 41 years of this teaching experience, what outcomes, because as on today we are talking about the outcomes of teaching, outcome-based education, everything, several things, okay? Therefore, first, my observation is that we should impart the knowledge. As several times in the class I will talk, knowledge is different and wisdom is different, okay? Therefore, as a teacher, we impart knowledge. When knowledge is only sufficient, we should have skills. Like we should, in the laboratory, we should do something, skills. And apart from this knowledge and skills, we should get the outcome of the teaching, which is the attitude. Most of the time, I will, for perfection, I will expect perfection from everything. That may be the reason, some issues. Therefore, 99% efficiency also I will not. We should expect 100%. And we should not be any, should not be here and there, plus and minus. Therefore, attitude towards something, towards subject or whatever it may be, and behavioral aspects are very, very important with respect to these outcomes of the teaching. And one more thing, one should have the urge. One should urge to solve the problems. And restlessness, we should not have any satisfaction. Therefore, restlessness is the prerequisite for innovation. When you are happy, we cannot do anything. We'll stop there itself. That is what I observed. When we think that I can do better, okay, if we want to do better, several ways will appear. I'm happy with only one way, we will stop there itself. Therefore, thinking I can do better, switch over our creative power, it will. And one more thing is that mindset changes the creativity. When you are having some mindset is there, we can modify, we can change, then we can learn, able to do some good things. And most of the time, you will see some people are very successful. That is, successful people, they will think and act more effectively That is only the basic difference between successful and not successful people. And one more thing, for the motivation, everyone should require some motivation. Dr. Abdul Kalam says, all birds find shelter during rain, but eagle avoid the rain by flying above the clouds. Therefore, with this one, problems are common. I will get some problems are very common, but attitude make the difference. How you will act. Therefore, based upon this is my thing what I got. Now come back to this thing. That is why I will talk about another 5 minutes. Therefore, first of all, the way I'm here, Matru Devo Bhava, Pitru Devo Bhava, my parents I want to give tribute, and my teachers, Acharya Devo Bhava. In this one, by two teachers, I can say, that is one, when I was doing my B.Tech and M.Tech from Usman University, when I'm doing my M.Tech, my professor P.S.R. Murthy, he was my supervisor. He actually came from NIT Warangal in 1977. Therefore, his teaching was so excellent. I fascinated. I used to think NIT Warangal, all the teachers will be like that. At the REC Warangal, he was very, very, very good teacher. I was very fortunate to work under him. Therefore, after getting the teaching assistant job here at NIT Warangal in 1981, after coming here, I don't know anyone. And how to teach? At the time we are having several training classes, several things are there, but at the time, no. How to teach? Therefore, I took, my role model is a Professor P.S.R. Murthy. He's so nice, he will teach. Therefore, still my practices of teaching is like Professor P.S.R. Murthy only. Still I'm having some contacts with Professor P.S.R. Murthy. And he has written some books also on power systems. Okay. One more teacher, that is my beloved, very, very beloved, that is Professor S.C. Srivastava. Still I will think, if I would not gone to IIT Kanpur, my maturity levels, not that much. In the IIT Kanpur, most of the time I will ask the students or anyone, go to IITs. You will get, not only from the teacher, from the students also, how they are working for, several things. Therefore, it will change our mindset. Therefore, everyone will not get an opportunity, but whenever you get some opportunity, it is better to try the IIT Kanpur. And so, Professor S.C. Srivastava, so nice man, 3 years, I made out some mistakes during doing my research work and all that. He never got any angry. I never seen. And he was suffering some problem and all, I never seen. Every day, if he got out of station, not an issue, but he was very active. Anytime I can go and interact with him. And recently I asked him, sir, have you got anytime angry? Because I never seen, our curiosity is there, whether you will get any angry or not. He said, once or twice he get angry. Because when he was deputy director at IIT Kanpur, he said, due to some issues, okay, he got once or twice, only he told. I asked this question before all the participants in one of the workshop. Therefore, this is the thing, the teachers will mold the shape of the students. But we should have some enthusiasm to learn. Okay? Thank you very much, sir, for giving me this opportunity. And remaining thing, my journey and all that, I will talk tomorrow. Thank you very much for this.
Thanks a lot, sir. We are obligated by your presence in the department and wish you a hearty superannuation, sir. Now, it's very important to know about the dignitary we have with us today in order to appreciate his greatness. Thus, I request Girdhar, sir, to show his presence on the dais and tell some few words about M. Ramamurthy, sir. Girdhar, sir, please.
Very good morning, all. It's a great privilege for me to introduce about our chief guest, Professor Ramamurthy Garu. Sir has obtained his BE honors from Andhra University in 1957 and ME from IISc Bangalore in 1959. He obtained his MASc and PhD from Toronto University in 1965 and 1967 respectively. He was a Commonwealth Fellow at Toronto University from 1964 to 1967. On returning to India, he joined IIT Kanpur as a faculty member in the Electrical Engineering Department, where he became professor in 1972. He established for the first time in India a graduate program in power electronics at IIT Kanpur in the year 1968. He has supervised more than 12 doctoral projects during this period, and he was associated with many sponsored research activities for industries like BHEL and Hindustan Steel Limited. In 1977, he joined Hindustan Brown Brewery Limited, now it is ABB, as a chief of research. He was responsible for the development of a number of prototypes in switchgear, relays, and instrumentation. He joined the Central Power Research Institute as its first Director General in 1983. He retired from the service in 1994. During his tenure, CPRI became a well-recognized research and testing laboratory in the power sector. Dr. Ramamurthy took over as a director, ERDA, in June 1995 and demitted his office as director on 31st October 2006 after completion of his contract period. Professor Ramamurthy took over as an advisor, ERDA, from 2006. He worked as a visiting professor in a number of universities abroad, which include University of Sydney, Washington State University, Worcester Polytechnic Institute, University of British Columbia, and many others. Professor Ramamurthy authored 6 books on thyristors, CAD of machines, reactive power, power system protection, electric machines, and hydropower generation, and edited 1 book on power plant instrumentation. Recently, Professor Ramamurthy authored books like Applications of Power Electronics in Utilities and Industries as well. He is a fellow of IEEE and fellow of Indian National Academy of Engineering. He is recipient of number of awards which include Vasvik Award, Bimal Bose Award, Jawaharlal Nehru Birth Centenary Award, Vishwesvaraya Memorial Award, Pandit Madan Mohan Malaviya Award, National Design Award, Power Engineers National Award, IISc Alumnus Award, NPSC Award, Lifetime Achievement Award from IEEMA, and was the distinguished lecturer for Region 10 of IEEE. Recently, Hari Om Ashram Prerit Lecture Award, and also many awards he has received. Professor Ramamurthy has a patent on field-oriented control of synchronous motor. He has published more than 200 technical papers in reputed journals and has been actively associated with the power sector for over 3 decades. Under his directorship, ERDA received many recognitions and accreditations and has become one of the few self-supporting research and testing institutions in the country. During his tenure at ABB, CPRI, ERDA, he has supervised 10 doctoral projects as well. He has been awarded honorary life membership of Society of Power Engineers for his contributions to the power sector. Thank you very much.
Thanks a lot, sir. But greatness is something which cannot be bounded by words. Thus, I request Vinod, sir, to continue the description.
Just I will talk about only 2 points. I actually forgot. We are having a stalwart, Professor M. Ramamurthy Garu. Just I want to talk about 2 things. 2 minutes only I will take. When I took over as a head in 2007, I invited sir as a chief guest for the inaugural function of the students' inaugural that association. In that one, when at the time, we planned at about 11 o'clock to 1 o'clock, but at the time, to some issues, director has given only the time, 12 to 1, only 1 hour. Therefore, at 12 o'clock we started. It went on up to 1 o'clock, 1:30. And this type of auditorium or conference halls, seminar halls were not there at that time in 2007, where I'm a small seminar hall. We used to call that seminar hall as a new seminar hall. The students are, up to even though they missed their lunch, they waited up to 1:30, and the conference, the seminar was very full. I have surprised myself. And one more thing, still I remember myself in 2007, what one of the word, that is, in any organization, we should learn something new daily. Otherwise, we should leave that organization. That is what Professor M. Ramurthy garu. And one more thing, that is, I think in 90s somewhere, 93 or 94, at IIT Delhi, there was National Systems Conference. Sir was he was chairing. He was mentioning, if you want to chair a session, we should have some qualities. Therefore, at the time he was mentioning about his PhDs and all that, now we are talking about in protection, that is numerical processor, protection, numerical release, etc. and all that. Sir has done in 50, his PhD work at the time in 50 itself, we will know only electromagnetic release. Sir was mentioning, at the time, examiner was asking, sir, that is, Professor M. Ramurthy garu, in which world problem you have done? That is the caliber of Professor Ramurthy. Thank you very much, sir, for this.
Thanks a lot, sir. It's time for the very much awaited moment. Now I request Professor M. Ramamurthy, sir, to address the gathered audience. Sir, please. A big round of applause is appreciated.
This is the problem of inviting old people for inaugural functions. I'm sorry I'm giving a lot of trouble to young people here in holding me to go up the stairs. Professor Director Ramana Rao, Professor Vinod Kumar, Professor Narasimha Razu, I'm very happy to be here today. For some reason, I feel coming to NIT Warangal is like homecoming for me. Many people may not know that in 1959, immediately after my completion of the master's degree in Indian University of Science, I got an appointment letter here from here as a lecturer in the Department of Electrical Engineering. At that time, the REC was being organized inside the Polytechnic in Warangal. Well, fortunately or unfortunately, I also got an appointment letter from IIT Madras, which just started recruiting people in '59. So I preferred to go to IIT and did not join here. Maybe I missed something, but also gained something also. I am very grateful to Narasimha Razu for inviting me to come over here for the workshop as chief guest. About 2 weeks ago, at that time, I told him that I am very desirous of visiting NIT. Of late, I have not come here, but I came several times here. One of my close friends, Professor N. Rama Rao, I don't know, many people may not know him. he was here, and we both were contemporaries doing PhD. I was doing at IIT at University of Toronto, and he was doing his PhD at the University of Wisconsin in USA. And he joined here, and I was at IIT Madras, and I used to come here to meet him and discuss with him various topics. That is why I always feel in my heart that visiting NIT is like homecoming for me. So when Professor Narasimha Raju invited me to come over here for this function, I was a bit hesitant because my health is changing almost every day. Today I'm all right, luckily, and tomorrow I don't know. So at that time I told him that I'm very happy to accept your invitation, provided God helps me to be all right on 30th of January 2023. Luckily, I am here before you, and I am happy to be here. And I see a lot of progress in NIT campus. And coming to Warangal also, the road itself has been very much improved now. And it took me almost about 2.5 hours to come over here. I still remember when I was advisor to Crompton Greaves R&D Center in Bombay, they wanted to come over here for recruiting people for their R&D division. And they asked me to help them to identify the proper candidates. So we started coming to Warangal. At that time it was still called REC, I think. It took me more than 10 hours to come over here because there was some agitation going on the road, and our car was held up. And by the time we came here, the students were not there. So the whole mission did not accomplish anything. But now it is a different story, beautiful road, and we came in time. I am also happy to congratulate the EEE department here for organizing the felicitation program for Professor Vinod Kumar by organizing this two-day workshop. So Professor Narasimha Raju and the EEE faculty here, I want to congratulate them for thinking of having an academic type of felicitation program for Professor Vinod Kumar. Professor Vinod Kumar is retiring after a dedicated service of 41 years in the department. He is retiring tomorrow, and I take this opportunity to wish him all the best in his retired life. Definitely, I am sure that he will continue to provide his services to the academic institutions, whether it is NIT or any other place, as long as he can. I wish to tell him that the physical health depends mainly more on the mental health. If the person is engaged in some technical work of his choice, he will continue to be physically all right. When people ask me that, how are you? I say that for my age of 87, I seem to be all right here. If the very fact that I am standing here before you shows that physically, of course, I am not very strong as I was earlier, but I am able to do my activities as much as possible. Even now, I review papers, review theses which are sent to me, but the process has become slow because I am not able to read continuously because of my strain in the eyes. So, Professor Vinod Kumar, my suggestion to you is that you continue to be active professionally and provide your services to the people. And I also wish all the best for Mrs. Vinod Kumar, who is here. And I hope you will have a good, efficient, purposeful, retired life. Thank you very much. As suggested by Narasimha Razu, I continue my address regarding this topic which is chosen for this two-day workshop. Okay, please. Nice meeting you. Thank you very much, sir. The topic chosen for this two-day workshop is emerging trends in power engineering. Okay. So you've got another meeting. Nice meeting you. I will come and see you in your office.
Please.
Before I leave. You're free counter, huh? Oh, outside. Thank you, sir. The topic for this two-day workshop is emerging trends in power engineering. I presume that this is electrical power engineering, not chemical or mechanical. And also, since it is being organized on the eve of retirement of Professor Vinod Kumar, I believe it is related to the education. Power engineering education. I hope I am correct here. Professor Narasimha Razu, this is emerging trends in electrical power engineering education. Is it correct? No. What I say, what is it our talk discussion here will be? But anyway, I am perhaps more concerned about the education pattern. The first thing is that remarkable changes have taken place in the electrical engineering education over the past many decades. It's not just a new phenomena. If I compare the type of courses I have studied as an undergraduate students in Engineering College, Kakinada, from 53 to 57, and now what courses are being offered, there is a remarkable difference. This change has taken place because of various facts. One is the technology available outside. And the main object of academic institutions is to provide the industries with students who are knowledgeable about what is happening in their own field so that they will be of some use. At that time, I am talking about 50s, most of the industries, when they take the student, they take them as graduate apprentices. BHEL, Hindustan Steels, Indian Oil Company, Coal India Limited, and even the private institutions like Crompton Greaves, BB's, ABB, Tatas, they all take them as not as regular engineers but graduate apprentices. The reason being that the people who are coming out of the academic institutions should not be permitted to take up regular jobs in the manufacturing units. Now slowly that thinking from the industry's side has evaporated. They want people to be directly useful to them. What will the academic institutions do? There are so many different types of manufacturing activities going on in the country. If you take electrical engineering per se, you have people manufacturing transformers, manufacturing switchgear, manufacturing electronic equipment, manufacturing protection systems. They all require different type of knowledge. They can't expect the university to provide the required amount of knowledge level to satisfy all these industries. I still remember when I was working at CPRI Bangalore, I was the chairman of the IEEE Bangalore section, and I took up a project with the permission of the IEEE to do some revision of the courses content for the academic institutions and give a copy to the Government of India and also to the AICTE. I consulted all the industries to find out a common pattern by which the training can be given to the students by the academic institutions. The common factor appeared to be zero. Every industry wanted the students to be taught so that they become directly useful to them without any further delay. So it's impossible. What is the role of an university? As per a very famous educationist of yesteryears, Alan Hochschild from UK, he wrote a book on the university. And he said that the purpose of university education is to provide basic tools to the students, not to train the student for a particular job. The object is that the student with the basic tools knowledge, he can go into the market and develop whatever is required professionally for him using these basic tools. Now these basic tools are changing with time. That is why there is a requirement for changing the course structure, which has been going on for the last few decades. And AICTE, I believe, gives out a list of courses and their contents to be followed by the academic institutions which are recognized by the AICTE. Now, so many technological changes have taken place. Now, the problem now is, are the teachers aware of the new technologies? For this, a proper type of interaction is required between the academic institutions and the industries. For example, when I was with IIT Kanpur from 1966 to 76, IIT Kanpur was the first in this country to allow its faculty members to go to industries and work there. It was not there, the concept was not there. The academic institutions thought that the industries do not understand the basic subject. They only know how to copy and make the designs borrowed from outside. The industries feel that these academic institutions are all theoretical and they don't do anything practical work. But I took up that opportunity. I began to work in summer at Tata Electric Company in Bombay. It was a great beneficial thing for me. I could learn so many things from those people. And I also gave back to them during my almost 4 months every year. I used to go continuously for 5 years. I could develop a number of relays, which they were manufacturing actually afterwards. And my students had the advantage that most of them got immediate employment after their degree in Tatas. So this is the advantage of the mutual interaction between the academic institutions and the industries. Both will get the benefits. The industry gets what they require with the proper knowledge, and the academic institution gets the benefit that their students easily get good jobs. If I remember correct, that most of the IITs have got national laboratory research facilities. IIT Kanpur has got the real-time software for power systems. IIT Bombay has got the solid-state device fabrication center. And these centers are supposed to provide free access to any faculty member coming from outside. I don't know how many academic institutions are utilizing this opportunity to send their faculty, maybe not many, maybe 1 or 2 per year, to work in these centers here and get good knowledge about the latest trends in power system control and also in solid-state device fabrication. Now, what are those technological developments that have taken place in the last 2 decades, which is affecting the educational pattern in engineering, electrical power engineering education? Let us take, for example, solid-state devices. In 1967, when I started teaching power electronics at IIT Kanpur, the only device available was thyristors. That's why my first book on thyristors was basically related to thyristors. But now, the requirements has changed now. We have so many other devices which are more powerful and easy to implement in electronic circuits, better than thyristors. So there's no point in teaching much about thyristors at this time. And also the silicon concept is changing now. Most of the solid-state devices are replacing silicon with better devices. For example, the GaN devices, gallium nitride device, has got a higher temperature range of operation. Similarly, silicon carbide. These are being used for making the devices more compact and also more powerful. So these should be at least elementarily taught in classrooms, and the teachers must become familiar with these new devices. For example, the latest one, which is not yet come to the market, but laboratory type, called silicon integrated transistors. They have what is called as the internal regeneration, which none of the devices like bipolar devices or these thyristors. Thyristors have got regeneration facility. MOSFETs, they don't have regeneration. And therefore, their short-term current rating is very much low. When people wanted to develop solid-state breaker, which they are not still successful, because of the problem with these existing devices, that they cannot carry fault current for more than one cycle. They get burnt. But now this device, SIT, it has got internal regeneration. And therefore people are trying to use this device to replace mechanical breakers. So maybe in another decade's time, this whole switchgear concept will be changed. And you can utilize these SITs of large power ratings where the short-term thermal current rating is 40 times the normal current rating. So you don't more require a mechanical breaker, and the current interruption takes place within the first zero crossing. So this is how the technological changes have taken place, and the industries who are using these new technologies here, they expect the students to really know all these things. So this is the change that is required. Now, digital techniques have come, and phenomenal developments have taken place on ICT, information and communication technologies. Now we have to make use of these new technologies for remote control. These have not entered into textbooks still. So they will become a normal practice for industries, and industries expect people to know about these things. So these are some of the changes which have to be incorporated into the curriculum by changing the contents of the courses. And for that purpose here, the faculty also must be conversant with those technologies, which can happen if there is a mutual cooperation and understanding between the academic institutions and the industries. I am very happy that we have among the invited speakers today for this workshop, there are people coming from the industry, and they may perhaps be able to tell more about the industrial requirements and how they can be satisfied by the changes that take place in the curriculum level. The microgrids, use of renewable energy resources, and inverter-based DERs, how the interconnection takes place, how the microgrid gets islanded without problems, without jerks, how to improve the power quality. These are some of the things perhaps should be taught, at least at the final year level for the industries. I'm happy that this workshop is being arranged as a send-off gift to Professor Vinod Kumar, and I wish all the best for all of you. Thank you very much.
Thanks a lot, sir. We duly appreciate the tremendous number of enormous stones you have turned in a very short span of your lifetime, sir. We are very pleased to have you all with us. And sir, I'm really inspired by you as you have authored so many books. It's time for solidifying this remarkable gathering. Therefore, I request Registrar NITW, Govardhan Rao sir, to join us on stage. And I request the faculty members to felicitate our honorable chief guest. A big round of applause. Sir, now I request all the faculty members of electrical department to show their presence on stage and felicitate our guest of honor, Vinod Kumar sir. I also request the faculty members to present a kind memento. A big round of applause. Thanks a lot, everyone. It was a remarkable beginning of this knowledgeable session. And surely it was not possible with the efforts of so many people behind it. Therefore, I request Professor Anil Nayak sir to present his vote of thanks. Sir, please.
Good morning, ladies and gentlemen. It is my privilege to have been asked to propose a vote of thanks on this occasion. On behalf of entire fraternity of the Department of Electrical Engineering, NIT Warangal, I extend my most sincere thanks to our chief guest, Professor M. Ramamurthy Garu, former Director General, CPRI Bangalore, who spared time from his busy schedule to grace the occasion. I extend a very hearty vote of thanks to our guest of honor, Professor N.V. Ramana Rao Garu, Director NIT Warangal, and Professor D.M. Vinod Kumar Garu, Professor Electrical Engineering Department, for attending this function from their busy schedule time. I also thank you to Registrar Sir, all the deans, HODs, and faculty members for gracing your presence and grand success of the event. A big thank you to our faculty colleagues for their constant support and guidance. We definitely would not make it this far without your support. Last but not the least, my deepest sense of appreciation to all the participants and students of NIT Warangal for making this function grand success. Thank you very much.
Thanks a lot, everyone. It was very nice with this remarkable event. Now, myself, Dev Vyas, the master of the ceremony, takes your leave and request everyone to stand up for the national anthem.
जनगणमन अधिनायक जय हे भारत भाग्य विधाता पञ्जाब सिन्ध गुजरात मराठा द्राविड उत्कल वङ्गा विन्ध्य हिमाचल यमुना गङ्गा उच्चल जलधि तरङ्गा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
So all the participants requested to stay back for within 5 minutes. Your next session going to be start.
Technology associated with various channels, IEEE transactions on industrial electronics, industrial applications, transportation, electrification, IEEE Journal of Emerging Selected Topics in Power Electronics. So many are there.
Thank you very much.
Please deliver your session, please. Am I audible, sir?
Yes. Actually, you need to turn off your mic because the voice is reflecting back to everybody.
Yeah, yes, sir.
Okay.
Yeah. Please, sir, you can share your screen if any. Please share your screen, sir.
Yes. Okay, so can you see the PPT?
Yes, sir.
Yes, sir.
And it is moving. Slides are moving.
Yes, sir, it is moving.
thank you and good morning. Welcome everyone. So my name is Akshay Rathod. I am presently in Singapore. I will be presenting a lecture on wireless charging technology, some fundamentals and requirements for wireless power transfer, and just I will share one circuit topology that can do multifunctional charging. And first of all, I would like to congratulate Professor Vinod Kumar of NIT Warangal to successfully finish his long years of service to NIT Warangal in terms of teaching research and mentoring the students. And not only to NIT Warangal, that is a contribution to the country itself because NIT Warangal is a institution of national importance, and his contributions are undeniable. And basically, personally, I know him very well. He's very social and a pleasant personality. It has been honor to meet him, know him, and work with him through Spark project and through Gyan programs and through various conference activities. So congratulations and thank you very much for mentoring all of us and hoping for your guidance in future also. So I would just start with this. In honor of him, I just thought of delivering some knowledge on wireless power transfer. So we will go through some merits of wireless charging and what is the major application of wireless charging or wireless power transfer. We'll study classification of it and some basic fundamentals that all must know before designing a wireless charging system or wireless power transfer systems. And after knowing some components and their requirements, as I said, we'll just share one topology that can do multifunctional charging of an electric vehicle. Okay, so from this slide, we can see that one is plug-in charging, where you can see a special connector. Okay, this connector we need to plug in on the car. Okay, and then basically, so this connector is through the grid, connected to the grid. Okay, so once it is connected to the car, then AC power converted to DC power through the onboard charger, and then basically it charges the battery. Okay, yeah, it charges the battery. So this is onboard charger and plug-in system. And here you can see the wireless power transfer system where there is no plug-in. Okay, there is no plug-in. Now this is an underground system. So there is a transmitter coil, which is a magnetic coil or magnetic pad that is buried inside the parking lot. Okay, you are not able to see it. Okay, it is inside the parking lot, and this is the converter, which is either inside the wall or basically it is just hanging at the parking lot. So it has one high frequency converter that is converting 50 hertz signal into around 90 kilohertz signal. And then why this is required to convert low frequency to high frequency, so that the coil size can be shortened or coil size can be made smaller or high dense. Okay, otherwise 50 hertz coil will be quite large, but 50 hertz or 100 kilohertz coils will be very small, and that's why we want a smaller magnetic size or a smaller coil size, so that it can come on the parking lot as well as it can come on the vehicle. So another coil is on the vehicle, basically on the bottom of the vehicle. So once we have a signal available at the transmitter of a resonant frequency through some resonant tank, it will have some resonant frequency. Okay, so the receiver will pick up those signals. The frequency here also there is a resonant tank. Okay, so the resonant frequency on receiver side is same as the resonant frequency on transmitter side. so that the two coils or two magnetic pads can be tuned. Okay, so the receiver coil can pick up the signal, and then those high frequency AC signal can be converted to DC through a rectifier, and then it charges the battery. Okay, so here the entire power electronics is on board in the plug-in charging or conductive charging, but in wireless charging, half of it off board, which is on the ground, and half of it on board. Okay, transmitter side is basically off board and receiver side is on board. Okay, but this is wireless, it is not plug-in. Okay. Okay, so I will just play one video, and so that we can understand a few concepts from that, and then we'll go through components of it one by one. Uh, can you hear the volume? Can you hear the volume? Can some you can hear the volume also? Eh? Okay. Uh, now? Okay. Okay, so this video is from United States Department of Energy as well as Oak Ridge National Laboratory. So it is quite authentic.
Wireless power transfer is an innovative approach using magnetic resonance coupling of air core transformers designed for today's growing plug-in electric.
Okay, so first of all, you can see that wireless power transfer is just like a basically air core transformer. So the transmitter coil side of the transformer, and instead of a magnetic ferrite core, it is air core. Through air core basically, and they depend upon the magnetic resonance. That's why we had basically two resonance circuit on transmitter as well as a receiver, primary and secondary. So it is just like a transformer technology.
Vehicle market. This technology can provide a convenient, safe, and flexible means to charge electric vehicles under stationary and dynamic conditions. Plug-in electric vehicles are burdened by the need for cable and plug chargers, galvanic isolation of the onboard electronics, bulk and cost of this charger, and the large energy storage system packs needed. With a system where you have to physically plug in, there are a number of occasions where the owner could very well forget to charge the vehicle. For stationary applications, like charging of plug-in electric vehicles at home, Oak Ridge National Laboratory's innovative wireless power transfer technology adds a convenience factor compared to actually plugging in, which means the vehicle will have a full charge every morning. Electric vehicle charging must be safe, compact, and efficient.
Okay, so you can see clearly that it is written that the efficiency is 91%. So it is clear that because of the air core, there is a leakage, because whatever the energy is coming from the grid to the transmitter or the primary coil, the same energy is not transmitted to the receiver basically. Okay, so there is a leakage. Even if we have a magnetic core, magnetic coupling, then also there is a leakage. Okay, 1%, at least 1% leakage. That's why we have a leakage inductance, right? Here the leakage is higher because there is no magnetic coupling, but there is an air core, and the gap is also quite large, around 25 centimeters. Okay, yeah. So that way, because of the high leakage or poor coefficient of coupling, generally in magnetic core, the coefficient of coupling is around 96%, 98%. But in air core with the 25 centimeter gap, the coefficient of coupling M is generally 21, 23%. Okay, quite low. And because of that, leakage is high and efficiency is less, 91%. Efficiency will even be less if we don't use compensation or resonant circuit. Resonant circuit helps to improve the coefficient of coupling or recover the leakage energy. Without that, this efficiency will be even less. Okay, so this is one major drawback of wireless power transfer or plug-in, that there is a convenience. Okay, but convenience is there, but efficiency is poor because of poor coupling coefficient or higher leakage.
In order to be convenient for customers. By reconfiguring the transformer and altering the resonance frequency, energy is transferred to the battery with lower energy losses and with fewer demands on the primary circuit by the rest of the transformer system. The Oak Ridge National Laboratory discovery shows that sufficient power for the battery can be transferred from the primary to secondary circuits without significant energy losses if the operating frequency is set between 50 and 95% of the resonance frequency of the circuit. The electrical power is then transmitted to the chargeable battery, which is electrically coupled to the secondary circuit through the air core transformer. Some advantages include reduced energy losses during transfer of energy to the battery, a charge potential that is relatively unaffected by up to 25% misalignment of vehicle. Other receiving components draw less power from the primary circuit. These advantages allow wireless power technology applications to expand at the workplace and beyond as the demand for electric vehicles rises.
So you can see that at the industry area, at the airports, where the large number of parking happens, basically, there you cannot have a plug-in charger, so many plug-in chargers. Otherwise, it looks very awkward, basically, wires everywhere. It becomes unsafe. Okay, but having a wireless charging infrastructure, they can just park their vehicle. You will not see any cords, no wires, nothing. Just a pad will be there basically on the ground, and your vehicle will start charging. So it doesn't look that bad or ugly basically, but it's quite pleasant to have a wireless power transfer infrastructure when at the airports or at the industry where or at the commercial parking lot where large number of cars are parked.
For vehicles that operate over a fixed route, such as buses and shuttle vehicles, wireless power transfer means that a smaller battery pack can be used. In the traditional system, the battery pack is designed to accommodate the needs of the entire route or shift. With wireless power transfer,
Okay, so this is one major application that America, South Korea, they are focusing on, and China also probably, and this has opportunity in India also. That what happens that in electric buses, because the buses has to start early morning, and then they like the buses that are used for local transportation or even for intercity, they go back to the garage after quite a long hours of driving from morning to evening, right, or the late night. So if a bus has to drive for 18 hours like this, like local transportation, right, then they should have a very large battery pack inside of large energy storage. Okay, that makes that makes basically buses quite expensive, because I think that you guys know that 50% cost of the electric vehicle is coming from the traction system, which is the battery, inverter, and motor. And out of this 50%, 50% is just battery itself. So generally, the cost of the battery is generally 20-25% of the cost of entire vehicle. Okay, so if you increase the battery size, then vehicle cost will increase significantly, as well as the weight of the vehicle, because batteries are very heavy. Okay, so this is not feasible basically, that having a bus is running 19 hours. Otherwise, without recharging, otherwise you have to bring back the bus to the garage first. Okay, so so this is opportunistic charging, that we can use very low power battery, low capacity battery, and at every bus stop which comes after 1 kilometer or less, where the passengers get in or get out. So during that time, the bus can get a bulk charging and then go to the next stop. Then again bulk charging, go back to the next stop, and then finally go back to the garage. So that way, instead of having the large kilometer capacity to cover the hundreds of kilometers, you need only, the battery capacity to cover from the garage to the first stop. Okay, maybe 10 kilometers.
The battery can be downsized because it can be charged when the vehicle stops on its route. A rental car shuttle bus, for example, can charge when it waits in the terminal and again when it waits at the rental car place. Thus, the battery only needs enough charge to get to the next stop. This decrease in battery size means significant cost savings to electrify the vehicle. This technology enables efficient opportunity charging stations for predefined routes and planned stops, reducing downtime. Charging can occur in minutes. This improvement also eliminates the harmful emissions that occur in garages while buses are idling during charging.
Okay, so basically we have a very strong local transportation all across India, and that way we cannot have buses, each bus of basically 19 hours of capacity in the battery. That way we will need to buy lot of lithium ion material or battery packages from overseas, which is very expensive, as well as their replacement backup plan. Okay, that is very, that is not a feasible plan. But this opportunity is charging, that every bus stop you can have a bulk charge and the bus can run. That can make the local transportation feasible through wireless power transfer. That we need only a small capacity or a small size battery. Now, so far we discussed basically stationary charging, that during charging the bus or the car is stationary, not moving. Now the next phase is dynamic charging, that USA has tested also recently in Oak Ridge National Laboratory.
In larger cities, dynamic charging offers an even greater impact.
Okay, first of all, we all know that suppose we cannot go, suppose for example, from Hyderabad to Warangal, because it's probably approximately say 150 or 180 kilometers, right? But the Mahindra vehicles we have in India, the capacity is approximately 100 or 110 kilometers. So somewhere halfway you need to get down, or you need to stop your vehicle and charge it. And if you don't have a charging station, then you need to wait for charging for 3 hours or something if you don't get fast DC charger, right? So intercity driving is difficult if you do not have enough capacity, that we don't have right now, suppose Hyderabad to Warangal. And if you don't have a fast charging station in between that can charge your vehicle in 30 minutes, then you have to wait 3-4 hours. Okay. So to avoid that, generally it is possible that there is a possibility of wireless charging on road. Okay. On road. So that way, what happens that you are driving non-stop, and there is a wireless charging pad coming in between after every say 10 kilometer. Then your vehicle gets some kind of charge, and that way you get additional ability to drive, and then you can go from Hyderabad to Warangal. So this is on route charging or dynamic charging.
Utilizing existing infrastructure. As vehicles travel along busy freeways and interstate systems, wireless charging can occur while the vehicle is in motion. With this technology, a vehicle essentially has unlimited electric range while using a relatively small battery pack.
Okay, so unlimited range means basically, although the battery capacity is small, but on the way you are charging it, keeping it full always basically. And that way you can go from one city to another quite easily. Okay.
In-motion charging stations use vehicle sensors to alert the driver. Traveling at normal speeds, sensors establish in-motion charging. Wireless power transfer transmit pads equip.
So you can see that in this kind of thing, the ICT technology, infocom technology is quite important. That when you are very close to the charging pad or transmitter pad on the road, Then the sensor, wireless sensor basically will sense the signals. Right now you can see it is sensing the signal if you are within 1 kilometer range or something, and your vehicle should be smart and intelligent enough to receive that signal. Then you see on your dashboard, on your screen, that okay, you have been alerted or prompted that there is one wireless charging pad is coming, so that you allow basically your vehicle to get charged through that. Okay, and you can reduce your vehicle speed a bit.
Eventually energized to the negotiated power level based on vehicle speed and its requested charging energy.
Here,
Lower power when vehicle speed is slow, and much higher power for faster moving vehicles. Dynamic charging would allow electricity to supply a very large fraction of the energy for the transportation sector and reduce greatly petroleum consumption. Previously worrisome traffic delays now provide longer periods of charge while passing over in-motion chargers. Inclement weather such as rain and snow do not affect the charging capability. At Oak Ridge National Laboratory, we are working to develop the robust nature of wireless power technology to provide a convenient, safe, and flexible means to charge electric vehicles under stationary and dynamic conditions.
okay, so this way, what happens that if this on route charging is there, that avoids basically the long queue in the DC fast charging station. If you want to go from one city to another, then everybody will be waiting at the fast charging station rather than slow charging station. So there can be a long queue basically. But this on route charging will avoid that, because basically your vehicle will get charged automatically on the way itself, and you reach your destination from Hyderabad to Warangal, and then plug in basically at your home or at the institution, and then charge the vehicle. Okay. So on route charging, on in motion charging, on route charging, or dynamic charging helps basically not to stop for charging or avoid the long queue at the fast charging station. You can just drive basically with peace of mind from one city to another city without need of any charging or battery replacement. Okay, so these are some applications of wireless charging. In South Korea, there is a place, Newman Mountains or something, which is touristic area. There, if you do Google search, you will see that in that mountain area, they are having only electric mobility, and through that electric mobility and wireless charging system only, they are basically maintaining that touristic area completely. Yeah, in South Korea. Okay, so one major application is local transportation also, that we just discussed, that passengers can get out and get in during the bus stop at the bus stop, and that time the vehicle can get charged also. That way you can reduce the battery size to a very small value, extremely small. Okay, so wireless charging basically two types. Okay, basically two types. One is inductive, which we just discussed so far. Okay, the two coils, and another is capacitive, basically through the two plates. Okay, capacitor plates. So here also it is air core, and here also it is air core, and both are contactless. Okay, one is done through inductive, another is done through capacitive. So it is possible basically, but inductive is popular because inductive can go to a very high power range, hundreds of kilowatt. I think in Michigan, US, in Korea, in Oak Ridge National Laboratory, they tested basically stationary, like this is stationary charging with inductive coupling up to 100 kilowatts also. But capacitive coupling one has been tested only for a fraction of kilowatt, and its efficiency is also lower, around 80, 82, 85. But inductive coupling efficiency has been tested above 91%. Okay, so anyway, just for theoretical knowledge or academic knowledge, that yes, it is possible both ways, inductive and capacitive coupling. But inductive is for high power and it gets higher efficiency. Capacitive coupling is for low power, less than a kilowatt, and efficiency is lower. Okay, and we have just discussed another classification. One thing is basically mode mode of transmission, which is capacitive or inductive. Another is basically that stationary charging or the dynamic charging. In stationary charging, the vehicle is parked, and in the dynamic charging, basically the vehicle is in motion, right? So what happens that in this case, it is pulse charge control. So when the vehicle is coming closer to the receiver pad, there is a large bulk power transfer, not a small amount, a large bulk power transfer, and then you go to the and then you further drive until another receiver pad comes in. Okay, so this receiver pad, uh, this receiver pad in the dynamic power charging is broken into various pieces. So you can see that one receiver pad, then after 1 or 2 kilometers, you will see another receiver pad. After 1 or 2 kilometers, you will see another, sorry, transmitter. Receiver is on the vehicle, the transmitter. So you see transmitter 1, then after another 1 kilometer, another transmitter 2, then after 1 kilometer, another transmitter 3, after 2 kilometers, another transmitter, right? So what happens that they are not always energized. If they are energized, then basically they will develop flux and there will be a leakage of power, magnetization, all, and core loss, copper loss, and all, and there is a power loss. So you can see this K1, K2, K3, these are the circuit breakers. Okay. So you can see that whenever vehicle is coming closer to the coil, then you can see there is a wireless sensor or transducer. So because of the weight of the vehicle, then transducer or the wireless sensor basically will generate the signal. Okay, and that will basically close this K1, and then then the transmitter will be energized, and then receiver will catch the power. Okay, when it goes to the next, after 2 kilometers to the next transmitter, then again when the front vehicle wheels comes in contact, then basically it gets the transducer or the wireless signal basically will issue the signal. Okay, and then K2 will be closed, and then this coil will be energized. By that time, the receiver will come over the transmitter, and then it will pick up the signal. Okay, so that's how it works. They are not energized initially, like through the transducer, when like pressure transducer or so. When when the vehicle comes closer, then they get energized and transmit a signal to close the circuit breakers, and then close the loop. The coils get energized, and then the receiver gets signal, the bulk transfer. Okay. Okay. Now, like a plug-in charger, it is also possible to have a bidirectional power flow. So only thing is that both the sides we need to have the 2 quadrant switches, okay, 4 quadrant switches. So you can see that the switches instead of diodes, and here also switches instead of diodes. So you can see voltage fed dual active bridge. Okay, here also full bridge with switches and full bridge with the switches. Power can flow from here to here as well as in the reverse direction. Okay, so we can use basically wireless power transfer for vehicle to grid or vehicle to home application also. During vehicle to grid, the transmitter is on the ground and receiver is on the vehicle. And sorry, during grid to vehicle charging, and during vehicle to grid reverse power flow, the receiver now will act as a transmitter on the vehicle, and then the transmitter which is on the ground will act as a receiver. Okay, so the design should be done such that it can do bidirectional power flow. Okay, and we have to use bidirectional power electronics, which is instead of diodes we have to use the transistors. Okay, and the control system should have stability both ways. You cannot check the stability on the one direction grid to vehicle charging and use that for the vehicle to grid also. Okay, we need to demonstrate basically we need to demonstrate the stability in the reverse direction also. Okay. So now just review some fundamentals and some requirements of wireless EV charging systems. Okay, so these are the components of wireless EV charging. We have already seen basically that power electronics is an important part. Okay, on the primary side or the transmitter side, we have a high frequency converter that converts 50 hertz AC signal into 90 kilohertz high frequency AC signals. Okay, And we have a rectifier on board inside the vehicle, on the vehicle, that converts high frequency AC into DC. Okay. We have a resonant compensation network on the transmitter side on the ground, as well as on the receiver side on the vehicle. Two compensation network, resonant network. Okay. We need magnetic coils or pads. One is on the ground transmitter, one is on the vehicle receiver. Okay. Magnetic shielding also to cause any electromagnetic interference. Okay. And misalignment tolerance. For example, if the car receiver is not completely aligned or fully aligned 100% with the transmitter coil. Okay. So now let us just see the power electronics first. So here you can see that on the transmitter side we have a high frequency converter, and on the secondary side, on the receiver side or on the vehicle, we have the rectifier. So rectifier is quite easy. Okay. On the receiver side, since the source is AC, the grid, so you need an active front end converter that can basically maintain unit power factor in all conditions. Okay. So there is a rectifier, active front end rectifier, that converts AC into DC. Okay. And maintaining unity power factor in all conditions. And then that DC is converted to high frequency AC through high frequency inverter. The frequency of the inverter is around 80 to 90 kilohertz according to Society of Automotive Engineers SAE standards. Okay, 80 to 90 kilohertz. Then this high frequency signal passes through the coil. That's why the coil size becomes very small, because the voltage given to the coil is kilohertz rather than 50 hertz. Then the coil size becomes very small. Okay. Now we have a resonant compensation network. So because there is a large leakage between the two, okay, because there is an air gap of 25 centimeter and it is air core, so leakage is high. In order to compensate for the leakage, a resonant network is resonant circuits are connected on the primary as well, on the transmitter as well as receiver sides. Okay, so that the coefficient of coupling can be improved. The coils can pick up in better way from the transmitter. And a high frequency rectifier, which converts high frequency 90 kilohertz AC into DC. Okay, and a control system basically to control the power flow as the vehicle gets charged. Okay, yeah. So this is power electronics. And when it comes to the resonant circuits or the compensation network, there are various possibilities. Okay. And first of all, you can see that the power electronics can be voltage fed. So you can see the first four figures, VS, 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 VS. These are for voltage source converter. Okay. Similarly, the power electronics can be current fed also. You can see IS, 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 IS. Means the current from the source is constant. So it is current fed or current source converter. Another is VS, that the voltage from the source is constant to the circuit, which is voltage source converter. And you can see that there are various possibilities. Another is LC primary, LC secondary. Means two element resonant. Transmitter is also in series with the capacitor, receiver also in series with the capacitor. Another possibility, transmitter in series, receiver in parallel. So series resonance on transmitter, parallel resonance on receiver. Okay, now opposite. Parallel resonance on transmitter, series resonance on receiver. Now parallel resonance on transmitter, parallel resonance on capacitor. So there are four possibilities with two element resonant, LNC, two element. And the same is the possibility with current fed also. Okay. Now as a researcher, you have to decide that which one is better out of these 8. Okay. So this is topic of research, that which one is better. There is no thumb rule that this is better. Okay. As your power electronic circuit topology changes, okay, as your specifications changes, voltage rating changes, then the circuit will also change. You have to do mathematical analysis, and then you have to figure out which one is coming better. Okay. So with two element resonant, there are 8 possibilities based on voltage and current fed, and you have to pick up one best one. Okay. Just to give you some idea, it's clearly written that what are the points to be considered. One is compensation for the large leakage, means one which is improving your coefficient of coupling between transmitter and receiver despite 25 centimeter air gap. Okay. Number 2, which can avoid the circulation of heavy reactive power flow. You know that there is a transmitter coil, receiver coil, there is a large coil impedance, magnetizing inductance. So if there is a large inductance, then basically the circuit will draw large reactive power from the source. If you are drawing large reactive power from the source, then kVA rating of the supply will increase, okay, which is not good. As well as the ratings of the components will also increase, which is not good. Okay, so this is second objective, the circuit that will basically reduce the reactive power circulation. Okay, yeah. Another is losses due to reactive power. Anyway, that we are reduce the reactive power flow basically. So these two are the major objectives. Okay, there are more. We will see. This is another one. We all know that resonant converters we have seen in power electronics, they help us in soft switching of the components, and that reduces the switching losses. Okay, that reduces the switching losses. So this is another objective, that okay, since we are using 90 kilohertz switching frequency, already the wireless power transfer efficiency is less. With high frequency hard switching, you don't want to reduce further, so you can utilize the soft switching to improve the efficiency of the system. Okay, yeah. So these are the requirements that we just discussed. Improve the coefficient of coupling, maximize the power supply rating rather than the reactive power. Okay, minimize the kVA rating of power supply, soft switching of the semiconductor components, and reduce the kVA rating of the tank, which is the resonant tank, as well as the rating of other components. So this objective that we discussed are the goals to decide which compensation network is the best. Okay. Yeah, so this is just one mathematical analysis to mention you that how a different resonant tank can give different rating. So you can see that if we use LCC tank, and if we use LC tank, and if we use LCC tank, okay, 2 element versus 3 element, you can see that the voltage rating can be reduced to half. If voltage rating is half, then two benefits. One is cost of the switches will be less, okay, as well as the resistance will be less. Okay, yeah, you can see that the resistance is 950 milliohms, and here you can see it is 380 milliohms. Okay, less than half. You can see the rating of the switch, the cost of the switches is basically $60, and here you can see $30. The cost is half. Okay, yeah, but of course you have put extra capacitor, so you can see there is a extra cost of that capacitor you have to add. Rather than $8, now it is $21. Okay, yes, and because of the resistance has been reduced, you can see efficiency improved by 1%. Okay, up by 1%, 88 to 89. Okay, so these are, you can see that choosing a proper resonant tank can reduce the cost and improve the efficiency. And which are the objectives mainly here? Reduce the cost, improve the efficiency. Okay, now let's come back to the coil. Usually whenever we discuss about the coil, always we understand that that means circular coils. Okay, but that is not true. Okay, circular coils, you will see that circular coils are not good at all. Okay, yeah, so you can see there are several shapes possible. You can see one shape is like DD. One shape is circular. You can see the left hand side, the first one is circular, number one. Number C, you can DD. So this is D and this is D. Yes, I think I cannot use pen. So D and then D. Another is DDQ. You can see this is like Q and this is D and Q. Okay, DDQ. Another is bipolar pad. They are overlapping basically. Okay, yeah. Another is basically, this is called tailpipe something. Okay, we will see. So you can see that there are several possibilities that which one is better. There are several possibilities. Okay, so generally people, whenever it comes to wireless power transfer, everybody thinks of the circular pad, but there are many. Okay, so now you can see circular pad, and this is flux pipe. Yeah, so this pipe kind of thing is basically flux pipe geometry. So circular, DD, DDQ, bipolar, and flux pipe. So you can see that circular pad basically has low coefficient of coupling, okay, and very high exposed to EMF or EMI, okay. Yeah, but you can see the DD coil, DDQ coil, bipolar pad, tripolar pad, they all have high coefficient of coupling, and exposure to EMF is also low, okay. So these are much better compared to the circular one. You can see circular is the worst. Misalignment tolerant is poor, but you can see DDQ coil and a tripolar pad or flux pipe, they are tolerant to misalignment. Misalignment means the car is not coming in perfect alignment, the car receiver is not coming in perfect alignment with the transmitter, okay. Yeah, so many times the researchers in academia who are working on circular pad based wireless power transfer, they think that efficiency is not coming proper. So you can see clearly here that they have EMI loss there, their coefficient of coupling is low, and that's why efficiency is poor, okay. Yeah, so here you can see clearly that DDQ coil is coming the best, all right. Yeah, DDQ coil is coming the best, and there are more. I mean, there are more circular, not only circular, even the rectangular, square shape, sandwich, there are more, but this is just to give you an idea that it's not circular which is best basically, okay. Now this was all about the coil shapes, the transmitter and receiver for static charging, okay. Now let us see about the dynamic charging. Okay, in dynamic charging, what happens that on the secondary side, which is the receiver coil on the vehicle, is the same, like a simple pickup coil. Okay, yeah, but the transmitter on the road can be different. Okay, it can be W shape like this W, it can be U shape, it can be I shape, it can be S shape. Okay, like this. So we can see that E type. This is E type. Oh, sorry, the first one is AE, not W. First one is E. So you can see E type, U type, and W type. Okay, and I type and ultra sim. Okay, so there are various varieties. Okay, and you can see that this mg here, mg means milligauss. Okay, flux, leakage flux. So you can see that U type has a large leakage flux, 51 milligauss, W type 50 milligauss. Okay, but you can see E type and ultrasim type. This is ultrasim, I believe. I think this one, this segment 1 and 2, like this. So you can see that basically that they have basically quite less leakage flux. Okay, yeah. Because of that, you can see that they are designed for quite high power. You can see the ultrasim type, the pickup coil can have 21 kilowatt power. Okay, yeah. And since because I type has a better efficiency 80%, okay, and leakage is almost similar, so you can see its pickup capability is even higher, 25 kilowatt. Okay, so what we can see from here that ultra slim S type and I type is 0.3. That's why it has been designed for high power. Okay, it is having 80% efficiency for 1 centimeter gap only, but it's 80% efficiency with 20 centimeter gap. If you make a 20 centimeter gap in E type, then efficiency will be 70% or less. Okay, yeah. So I type is quite rough and tough, robust overall. Okay, yeah. Okay, so these are some merits. So like I type cost reduction is very less. Cost reduction is there, so its cost is quite less. Low EMF leakage we have seen basically, right? Because it is I shape, so it is quite fast to manufacture. Okay, Ultra sim time also we have seen very low leakage, okay, and both had high efficiency. E-type lower manufacturing cost, U-type higher efficiency for larger air gap. U-type 72% for 17 centimeter. Okay, leakage is high, 51 milligauss. So based on our application, based on our power rating and specifications, okay, having this kind of knowledge, we can design basically that, okay, if it is stationary charging or the dynamic charging, which one shape of the coils or magnetic pads will help us getting reduced leakage and a higher efficiency. Okay, now shielding. Okay, so generally shielding is done in order to reduce the EMI and EMC effect. Okay, so there are different type of shielding. One is metallic material shielding. Okay, another is magnetic material shielding, metals like aluminum. Okay, magnetic material shielding, resonant active shielding. It has resonant circuit and switches, MOSFETs like that. Okay, active shielding. Sorry, no, resonance is reactive. It is not resonance. Resonance is reactive means it is only passive component LNC, and active shielding means here you have the switches. Okay, so you can see that overall more or less all are good. Okay, metallic shielding is coming excellent at high power level. Okay, yeah, and active shielding and resonance shielding also giving good effect, low to medium power. Okay, active shielding is up to high power even. Eddy current loss quite low. Okay, but it is quite high because it is a magnetic material. Okay, yeah, no active source required, but active shielding has an active source required. Okay, effect on efficiency, here it is a bit reduced because of the eddy current losses. Okay, so overall you can see that the best that comes is basically resonant reactive coupling. No active source required, no additional switches required. Okay, high shielding effect also, and efficiency effect on efficiency is very low. Okay, so somehow resonant reactive shielding is proposed to be the best out of four: metallic, magnetic, resonant, and active. Okay, there are some existing development. When I was talking about South Korea, the KAIST, basically Korea Advanced Institute of Science and Technology, is the most active in wireless power transfer in Korea. Okay, and in the USA, ORNL, Oak Ridge National Laboratory, and Bombardier. Bombardier is now purchased by the Alstom. So Bombardier is Alstom now. Okay, they are using it for trams also. Okay, trams, the local transportations. Okay, and in Utah State University in Logan, they are doing wireless charging for buses. You can see there was a LinkedIn news also yesterday or today morning about wireless power transfer in Utah State University in collaboration with something. They have some Aspire Center. Yeah. You can see the switching frequency is 20 to 60 kilohertz. Okay, but it is still lower. Generally, the standard is 80 to 90 kilohertz. They are using different type of package magnetic pads: E type, U type, W, D, D, I, F, E, circular. Okay, yeah. So these are the existing developments. Okay, and misalignment happens. Not everybody is a good driver. That alignment is perfect. Misalignment happens. So generally, whenever we design the shielding, whenever we design the type, the size, shape of the coils, then we take care of this misalignment also. Okay, because if it's not taken care of, then misalignment basically will reduce the coefficient of coupling and then power transfer capability, reducing the efficiency, as well as it will overload the converter. Right, because what happens that load is the load. If you want to still transfer the same power to charge the vehicle, okay, the power taken from the source will be more. Okay, and that power will flow through the components, making them overheated. So that is additional burden on the components if alignment, if alignment is not perfect, if the two coils are misaligned, then it will put additional burden on the charger components that you already designed. Okay, if more power is flowing through them, then components can burn also, they can fail also. Okay, For the safety, motion sensors are needed. That okay, if any creature, lizards, cockroaches are going here and there, then probably immediately the wireless power transfer stops. Okay. Otherwise, you will see that lots of creatures, mosquitoes, lizards, cockroaches on your parking lot dying basically. Okay, which is again bad. So motion sensors are included. Shielding is included. We just mentioned. Okay, to avoid any health effect on health due to electromagnetic interference and electromagnetic signals. Okay. So in the future is more towards now like motors, power electronics, and I mean batteries are still the scope of research, but majority is quite saturated. In terms of batteries, people are looking for better battery material because lithium ion is very expensive. Okay, so people are looking for lithium sulfur, sodium ion, those kind of battery materials which can be cost effective, so that cost effective and less energy intense. Just for your knowledge, that making of lithium ion batteries is very energy intensive and more energy consumption than the normal lead acid batteries, and because of that lithium ion batteries are expensive also. Okay. So in addition to batteries, vehicle to infrastructure, ICT, ICT technologies are quite important to make a vehicle intelligent or smart vehicle. So that vehicle can communicate with the infrastructure for charging, as well as can communicate with another vehicle basically for charging. They can borrow basically charge from one another. Okay. But a secured communication system needs to be established to send signal and receive signal with the high value of trust. So ICT technologies are playing very important role, and actually wireless communication, sensors, networks. So in addition to power engineering, this area is also emerging area for intelligent transportation system or intelligent charging systems or intelligent EV charging infrastructure. Okay. So this was just first part of lecture about wireless charging. We discussed the merit and applications of wireless charging, their classifications, some fundamentals, components, and requirements. And then we'll just discuss one circuit topology uh, that we developed in our laboratory. And not only we used it for grid-based chargers, we use basically it for solar-based chargers and vehicle to grid reverse direction power supply to charge the 450 volt battery, high voltage battery, as well as to charge the low voltage 48 volt battery in India, like that. Okay, so we'll just go through that quickly. So multifunctional charger. Multifunctional charger means it has multiple capabilities. Okay, one thing that you can use it as a stationary charger, wireless. Everything is wireless. Okay, stationary charger. Okay, means grid-based AC charging. Overall, it is like a AC to DC rectifier doing unity power factor mode of operation, UPF. Okay, it can do DC charging also. Suppose example from the solar, and the same converter which is earlier working as a AC to DC converter will now act as a DC to DC converter. Okay. Another thing is synchronous rectification. Okay. What happens that if you are charging 450 volt battery, then you use simple diode based rectifier. But if you are charging basically, 48 volt vehicle batteries. In India, the electric vehicles are basically 48 volt. Okay, so if you use diode rectification for 48 volt, then it is going to be non-efficient. So for efficient charging at a low voltage, below 100 volt, okay, generally we use synchronous rectification. Okay. So if your charger is bidirectional, then you can use synchronous rectification basically for low voltage batteries. Okay, synchronous rectification gives higher efficiency rather than diode based charging if the battery voltage is low. Okay, less than 100 volt, which is the case in India. Receiver side control for dynamic charging. Okay, so far it was stationary, now it is dynamic. So I will explain that why receiver side control is required. Okay, and another is bi-directional operation for vehicle to grid or vehicle to vehicle power transfer. If another vehicle, another friend of you comes that okay, I'm out of charge and the charging station is too far, then probably he can borrow charge from your vehicle. Okay, so that he or she can go 5 kilometers and then charge the vehicle after reaching home. So you need a bi-directional capability for vehicle to grid or the vehicle to vehicle power transfer. So we developed a charging topology which can do all these 5 functionalities. Okay, so the idea was basically that generally first important thing that when you can like DC to DC converters are quite easy. You can number two DC to DC charging is okay. Synchronous based DC to DC charging is also okay. The secondary side is used instead of diode rectifier as a active rectifier. Okay. Similarly, resource side control is also again okay. That okay, the secondary side instead of diode you use the switches and like a dual active bridge you control them. That is also okay. Bidirectional, of course, a challenge, but of course in voltage fed dual active bridge people have done it. But important thing is that when it is connected to the grid, then unity power factor mode of operation is quite important, right, for the power quality. Okay. So we have seen that generally in the past people use boost of PFC, boost power factor correction converters. Okay, so you can see there is a boost converter here, right? Inductor, switch, diode, and then the battery. So this idea like came to our mind later after doing lots of work on DC to DC converter that okay, the current fed DC to DC converter because of the boost topology can also be used as a AC to DC converter, the same circuitry. Okay, yeah. So generally, what happens that when it comes to DC to DC, when it comes to AC to DC converter, the pulse width modulation of the switch is varying. You can see the pulse width is changing like a sine. Okay, and we are able to get sine current basically. Okay, it is also known as current wave shaping. Okay, so the way the sine magnitude is changing from 0 to peak, the duty cycle is also changing, the switch conduction time is also changing from 0 to the peak and then peak to 0, developing a sine current. Okay, yeah. So this idea, what happens that initially in our earlier research in 2010, 11, 12, we have basically in 2010 to 12 time we have worked on this topology. You can see there is an inductor which is current fed topology, and this is a dual active bridge, one primary bridge, secondary bridge, and like a DC to DC converter. But just now I have shown you that okay, a boost converter generally used as a power factor correction circuit, AC to DC. So the same basically can be used as an AC to DC converter also. Okay, so it is quite novel and quite a good idea that okay, if a circuit can be used as a AC to DC converter as well as a DC to DC converter, then you can charge your vehicle either from the grid, okay, or through the solar panel or from the other vehicle. So you charge it as a charge from the grid, then this converter will act as AC to DC converter with PFC feature, power factor correction feature, where it is basically solar based converter. Solar when it is a solar based charging, then the converter will act as a DC to DC converter with MPPT built in, maximum power point 20. Okay, and when it is connected with another vehicle battery for V2V, vehicle to vehicle power transfer, then simple DC to DC converter. Okay, and in the reverse direction it can act as a DC to AC converter, okay, for vehicle to grid power flow. Okay, and when it is 48 volt battery, this is 450 volt battery charging, then what happens that it acts as a diode rectifier. Switches are not turned on and on, only the diodes are conducting. But when it is a 48 volt battery, then the switches are conducting. Okay, then the switches are conducting. What is the benefit of synchronous rectification is that the synchronous rectification, if it is a 48 volt output, then the switches required are generally 75 or 80 volt switches. And the resistance of 75 or 80 volt switches is generally 3 milliohms, 3 to 4 milliohms, right? So if you do the conduction losses I square R, then R is milliohms, then what happens that the total loss is around 1%. But if it is a diode, then the diode voltage drop is around 1.5 volt. And suppose for example, 20 ampere is flowing. Then you will see that the power loss in all the 4 diodes is approximately 4%. Okay, So using the switches basically improves the efficiency. So you can use it as a V2G, as well as this can be used as a synchronous rectifier to charge low voltage battery. In dynamic charging, what happens that you don't have any control on the primary side, okay, because it is always live from the common source, okay. And once your receiver comes basically on the road during onboard on road charging or in motion charging, then when the primary energizes, the secondary will pick up the signal, okay. But how much current is picked up, you don't have any control over it. If it is a diode rectifier, it can be a very large current flowing through the rectifier, okay. Yeah. So in order to control that current, basically what you can do, you can basically control through the switches. So in case of dynamic charging, basically the receiver side rectifier is controlled to decide the charging current, I naught, okay, because every vehicle has a different battery, right, and every battery has a different charging current, right. The charger doesn't know who is passing. The Mahindra Riva vehicle is passing, or 450 volt Tesla is passing, or suppose 650 volt bus is passing, or truck is passing. Their charging current can be 100 ampere, your charging current can be 20 ampere, okay. So you need to control it basically through these switches, okay. So that's why all these 5 tasks are possible: grid based charging with unity power factor operation, DC charging from the solar, okay, with MPPT, or vehicle to vehicle, synchronous based charging for 48 volt EVs, receiver side control for dynamic charging, and bidirectional operation for vehicle to grid or vehicle to vehicle. Okay, so this single topology is able to do all. Okay, possible to do all. Only thing is that you need to design the control system which is stable in both the directions and for all the possibilities, AC to DC as well as DC to DC. Okay, now you can connect it either with the solar, with MPPT, or the grid. Okay, yeah. So now the charger benefits are, it is independent of battery specifications. It will operate as a synchronous rectifier for low voltage batteries and diode rectifier for high voltage batteries. Stationary, diode based charging, dynamic, receiver side control. It acts as a AC to DC rectifier with unity power factor for grid based charging and DC to DC converter for solar and vehicle to vehicle power transfer. Okay, yeah. And in the reverse direction, vehicle to grid. Okay, yeah. So single circuit is able to do. In case of solar to grid, solar to vehicle or vehicle to vehicle, generally it is a DC to DC converter with MPPT. So we have a paper in IEEE Transaction on Transformation Rectification 2015, and this operation is mentioned. On the primary side, we have LCC or CCL, and secondary side is series LC, simple LC. Okay, yeah. For synchronous rectification, we have demonstrated in this like this is a master's thesis. The link is for master's thesis, and he has shown it for 48 volt battery charging through the synchronous rectification, okay, and receiver side control through the secondary modulation, okay, yeah. For vehicle to grid operation, it is a reverse direction power flow, okay. So now just showing some experimental results. Okay, so here you can see VT is transmitter coil current and transmitter coil voltage and transmitter coil current. And VR is the receiver side voltage and receiver side current. So you can see that both are maintaining, because of the resonant tank network, they are maintaining basically the sinusoidal voltage and current. Okay, because of the inductance, you can see there is a phase shift in the voltage and current. Okay, but the receiver is picking up the signal quite nicely. Okay, yes, perfectly, like a perfect sign, because of the proper resonant frequency tuning on the primary and secondary side, or the transmitter and receiver side. Okay, and this is with misalignment. Okay, with 50 mm of alignment, misalignment. Earlier there is no misalignment, and now it is with alignment. This is a 20 centimeter of gap, and this is basically 15 centimeter of gap between transmitter and receiver. Okay, you can see this is DC voltage output. Okay, and this is getting signals to the switches. Okay, just shown for the one switch, and this is the charging current ID. Okay, okay. Now this is, you can see, this is for, okay, sorry. And this is the inverter output and this is the capacitor voltage. This is inverter output of the 4 switches. And you can see this is the capacitor voltage, VCS. Okay, VCS. This is VT, like this VT, transmitter voltage. Okay. And this is the getting signal voltage for switch S1 for the two cases. One is 20 centimeter of gap and another is 15 centimeter gap with 5 centimeter of misalignment. Okay. And you can see the source switching also, that you can see this is the charging current I note. And you can see source switching, that okay, the current started going down to 0 very closely, and then the rectifier current will start picking up. Okay, so switching losses are a bit reduced. Okay, switching losses are a bit reduced, that okay, voltage is going to 0, then the current starts conducting, and here the current is going to 0, and then the voltage starts building up across the rectifier. So rather than having a large switching losses, the switching losses are limited a bit, controlled a bit. Okay. Yeah. So this was for the rectifier diode secondary side. But on the primary side, you can see that the capacitor voltage goes down to 0, and then the capacitor will start conducting, the switch will start conducting. Okay. Even for the second case also, the switch voltage goes to 0, and then the switch starts conducting the current. Okay. Same thing for another case, that switch voltage goes to 0, then switch starts conducting. Okay. So source switching is achieved completely on the primary side, on the inverter switches, and on the secondary side, rectifier side, the switching losses are reduced. Not full source switching, but because of the resonance, the losses are reduced, switching losses are reduced. Okay. Now you can see the transient operation also. So right now this is for DC to DC part. Okay. So far what we discussed is for DC to DC part. So this VD and ID is the input. Okay. VD and ID is the input. You see input DC voltage. It is mentioned input DC voltage, and this I note is the output voltage, charging current. Okay. And this VB is basically the rectifier output voltage after rectification, which is same as the output voltage, we can say, or I note is the charging current. Yeah. Now this is the transient operation. We can see that when the step change is applied from half load to full load, you can see the transition is quite smooth. Okay. So here steady state results during transition shows that how the operation is smooth. So this is before transition, during the transition, and after the transition. Okay. From one steady state to another steady state, and with the transition, you can see it's quite smooth. No over voltage or no over current overshoot. So the switches are quite safer and stable. That's what I mentioned earlier, that the control system should be stable in all conditions, either it is AC to DC operation or DC to DC operation. Okay. Now let us see. So this was DC to DC. Now let us see AC to DC operation. Okay. The earlier the switch was conducting as a DC to DC. Now the switch is conducting. Now the circuit is working as a AC to DC, grid to vehicle charging. So major purpose during this is to maintain unity power factor basically. So there is a paper in IEEE transition power electronics, which is basically the same circuit is acting as a AC to DC converter. Okay. Yeah. So this paper has got a best paper award also. I mean, sorry, not best paper award total. I mean, the highlighted paper award means in July 2020 issues, the best paper in July 2020 issue. Okay. So you can see that, sorry, 2018, not 2020, 2018. Okay. So this paper was published in 17 and awarded in July 2022, July 2020. Okay. So now you can see that primary side, you can see the green signal is the grid voltage and yellow signal is basically the grid current. So you can see they are maintaining unity power factor. And this envelope kind of waveform is the voltage and current waveform through and across the switches. Okay. Yeah. So if we see one high frequency zoom version of this, you can see. So this is AC, very small value from here, peak value, and this is the IAC, the current. And you can see this envelope is like a sine, And this is the voltage, and this is the current. Current is flat because of the current source signal, current source feature. Okay, and you can see this is also zoom version near to the zero crossing. This is near to the peak, and this is near to the zero crossing. Okay, so you can see during the peak the magnitude is high, and during zero crossing magnitude is going down. Okay. You can see the transmitter coil and receiver coil signals. Okay, and this is zoom version. This is the again at the peak, and this is near the zero crossing. Okay, and this envelope is showing the AC to DC operation, the positive and negative. Okay, and you can see the source switching. The switch voltage is going down to zero, and then the current starts increasing. And when the current goes down to zero, and then the voltage starts increasing. Okay, so source switching is happening. This is the rectifier diode side, and you can see that okay, the current goes to zero, then voltage start building up, and when the voltage goes down to zero, then current start conducting. Okay, so rectifier diode and primary switches, they go through the source switching. And again, now during the transient condition, the circuit is operating from AC to DC rather than DC to DC. You can see there is a smooth transition. Okay, so you can see the zoom version. First of all, in the transition itself, you can see a smooth transition rather than any overshoot. So DC to DC was stable, AC to DC is also stable, and you can see that unity power factor mode is maintained throughout. Okay, unity power factor mode is maintained throughout. Okay, yeah, and so this is basically during the transition, and this is after the transition. During the next steady state value, you can see still unity power factor mode is there. So that's why I said that the major objective in AC to DC is unity power factor mode of operation all time. So it is happening always. Okay, with the stability. Okay. So generally the electric vehicle chargers are two-stage chargers, where the first stage is used for UPF and second stage is used, first stage is for UPF, unity power factor operation, and second stage is used basically to control the charging current, fast charging, slow charging. But here what I demonstrated is basically a single stage charging, basically. There's no intermediate DC link. Okay, so no PFC first and then the charging current regulation. Everything is done together. Okay, so generally instead of two-stage chargers, what we have is basically direct single stage charger that is controlling UPF as well as the output current. This charger category we have named as flexible chargers, means you can connect them to the grid, you can connect them to the solar, you can connect them to the another vehicle. Okay, so in addition to the plug-in charging, initially we have done this flexible charging or multifunctional charging on plug-in systems. Then what I discussed today is that it is applicable to wireless power transfer also. Yeah. So generally vehicles batteries are different. Overseas it is 450 to 650 volt, but in India it is 48 volt vehicles, like electric vehicles. So synchronous rectification is good for charging, for specifically for batteries in India. So the same charger is able to do because you need active charging, active rectification rather than the diode rectification. Okay, so that's all from my side, and thank you for patiently listening, and I will be happy to answer any questions. Yes.
Thank you very much for your valuable insights in wireless charging systems. So covering all basic and requirements of wireless charging. Static charging you have explained, dynamic charging you have explained, moreover in that segmented type, so which is very interesting. Pulse charging control as well as design and topologies for DC to DC, AC to DC operations you have explained. Moreover, flexible charging, much more, which is very important for the research, for the researchers. Safety aspects also we have covered. So it's very interesting and good research inputs you have provided, sir. We are very thankful for you, for your valuable insights in these wireless charging systems, which is booming nowadays, very important. Thank you very much, sir. 1 second, sir.
Yes, thank you.
Yeah. Yeah, thank you so much, sir, for taking your time and your kind acceptance to contribute to our workshop. And really so kind of you. Thank you, thank you, thank you, sir. Thanks a lot once again.
Thank you, Dr. Ali.
Yeah, thank you, sir. Thank you.
Thank you.
Professor Vinod Kumar sir conveyed wishes to you,
Thank you.
and also Professor Ram Murthy sir also came for us as a chief guest.
Yes, sir. Actually, they conveyed the wishes, and of course, they had some meeting, so they just left half an hour before. So on behalf of them, I am conveying their wishes to you. Thank you.
Thank you very much. Thank you.
Yeah, yeah. Thank you, sir. Thank you so much. Yeah. So, thank you, sir. Thank you.